Hello and welcome to College Algebra. We're going to finish off talking about properties of functions. So this will be part 2. We're going to talk about even and odd functions. Although one last thing we're going to do right before we go into that is we're going to do one more thing with maximums and minimums on the calculator. So if you look at these problems down here, you can see the instruction is to use a graphing utility to graph each function over the indicated interval and approximate any local maximum values and minimum values. Determine whether the function is increasing and decreasing. Round answers to 2 decimal places. So, approximate any local maximum and minimum values. So let's look at this 61. Turn the calculator on here. Wants us to graph it, so if I plug in 61, we have our function equals negative 0.2 x to the third minus 0.6 x squared plus 4x minus 6, and it wants us to graph it over a very specific domain, so I will go ahead and plug that into the window. Negative 6 to positive 4. And that may be enough. We may have to change our minimum and maximum to see it. Yeah, it looks like not low enough to see the bottom of this. Well, let's change our y minimum. Let's double it and see if that's good enough. That's pretty good. Now we'll take it down just a little bit further, but don't really need to go that high either. Beautiful. Okay. We can clearly see there's a local minimum and a local maximum value. You can just try and approximate them with the trace, but we can be a little bit more accurate than that because there are functions in the calculator for doing this. If you go into the calc menu, I believe it's actually short for calculus because the work for doing it is a calculus problem, but the calculator will do it for you. Let's see, if you go into second of trace, you get minimum and maximum. So we'll start off with minimum. It asks for 3 things. It asks for left bound, so you just scroll left and right until you're to the left of the minimum. Should be on the slope down towards it. And then a right bound, same idea, to the right of the minimum. Should be on the slope down towards it. And then a guess, just the closer you are, the faster your calculator will get there. It's probably pretty close there. So there we go. Negative 3.76. And then I'm just going to write the point. Negative 3.77. And then negative 18.89. That's the minimum. The maximum. Well, we go back into the menu. Second of trace. Get maximum. And I got to go quite a ways over here. You can actually type something in though, so let's say 1. That'll work. Actually, I already accepted that as well. Well, let's take it a little bit to the right here. Alright, a right bound. Then a guess. Let's get it right there on the top. It's got to be pretty close to that. Yeah. So maximum at 1.77, negative 1.91. So there we go. There are our 2 local extrema. At approximately negative 3.77 is the local minimum, and at approximately 1.77 is the local maximum. Their values are negative 18.89 approximately, and negative 1.91 approximately, respectively. And as far as if you want to determine where the function is increasing or decreasing, well, since we know where the minimum is, it's decreasing from negative infinity to negative 3.77, increasing from negative 3.77 to 1.77, and then decreasing from 1.77 to infinity. Although on that specific domain, I guess we could narrow that some. Instead of negative infinity, it'd be negative 6 to negative 3.77, and from 1.77 to 4. Alright, let's talk about even and odd functions. Here's the definitions. A function is even if f of negative x equals f of x. So if you replace the x value with its negative, it has no change to the function. That is, by the way, the exact same test we came up back with in Chapter 2, I believe Section 2.2, when we were talking about symmetry, because they do correspond. A graph is symmetric about the y-axis if you can replace x with negative x and there's no change to the formula. Same idea here. It's just called by a different name because we have functions now. A function is odd if f of negative x equals negative f of x. It means the graph is symmetric about the origin. And remember when we did that test back in Chapter 2, we would replace both x with negative x and y with negative y. So that's basically what's happening here. We're saying they're equal. If I replace y with negative y, it's the same effect as if I replace x with negative x. Notice there is no function analog for being symmetric about the x-axis. About the x-axis, like say a sideways parabola, would not be a function. It wouldn't pass the vertical line test. In fact, if you think about it for very long, you'll see pretty much the only function that would actually pass the vertical line test and be symmetric about the axis is the axis itself. Because this is the only thing that if you rotate around the x-axis, it's not actually going to give you a line down here when you have a line up here, or a curve or simile. So really, symmetry about the x-axis isn't really a possibility for most functions. So let's go back here and look at some of these and talk about whether they're even or odd. This is just a symmetry test, so it's actually pretty easy to tell from the graph. Notice this is symmetric about the y-axis. If you rotate it around the y-axis, it's the same shape. So this is an even function. Same thing here. This is neither even nor odd. Same thing here, neither even nor odd. This, though, is not even, because if you rotate it around the y-axis, this part would be over here. But it is odd. Remember, you can check odd by rotating 180 degrees flat on the page. So this would rotate over to here, this part would rotate over to there, be the same shape. So it is odd. This one's even, these two are neither. Let's look at determining some of these algebraically. So, we'll start off with 37 here. Is it even, odd, or neither? On a test, I would allow you to do a rough sketch and make an argument from there. Here, they really want you to use the formula. It's a fairly simple test. We do f of negative x. Plug that in, cube a negative, it's still a negative, so that's negative 4x cubed. That is not equal the original function, so it's not even. But if we look at negative f of x, that is literally a negative times the function, negative 4x cubed. That is equal that, so this is odd. How about this? Well, g of negative x. It's negative 3 times negative x squared minus 5. Order of operations, you square the negative, become positive, but then it gets multiplied by negative 3. Negative 3x squared minus 5. There we go. The exact same as the original function, so this is even. You might ask, well, does it just correspond to the exponents? Well, yes and no. Certainly, if you're looking at a polynomial function like this, and it only has even exponents, like this does and this does, it is even. And if it only has odd exponents, like this, it is odd. But something like this is neither, because it has an odd exponent and an even exponent. because remember a constant is 5x to the 0. 0 is an even number. But other things are even or odd as well, like absolute value. Absolute value is an even function. How about this though? If I look at f of negative x, I would get negative 2x on the top. On the bottom, absolute value of negative x is still absolute value of x, so that's no different. If I multiply negative times the whole function, I get negative 2x over absolute value of x. That's equal that, so this is odd. If you do the work on 46 and 47, you'll find those are both odd as well. So I suggest you go ahead and practice with those. But we're going to move on to our last topic of this section. We're going to talk about average rate of change. Here's the definition. The average rate of change of a function between two x values is just the slope of the line connecting the 2 points. So if I've got some kind of function, let's say I got, say, a parabola. And I have a point here, a point here. It's really hard to graph on this tablet. I might need to look at some better ways of doing it. And you have a function. Well, the average rate of change, the rate of change of the function will change as it's going if it's curving. Like this thing is going down very quickly here, less quickly here, it's flat here, going up, going up, going up more quickly, going up more quickly, etc. So its rate of change is changing, it's accelerating. But average rate of change, you just find 2 points and do the slope of the line connecting them. Because that'll tell you roughly what it's doing. It's just not the rate of change of the whole function. It's just the average change over a set interval. So all you do is you're given two x values, x1 and x2. You find the two y values that go with them, and then just do a slope calculation. So it's really nothing new as far as calculating. It's just slope all over again. So let's do a problem. Let's look at 66 here. Find the average rate of change of f of x equal negative x cubed plus 1. From 0 to 2, well, let's see. Let's do all of these. So let's find a bunch of function values. F of 0 would be 1. F of 2 would be, let's see, negative 8. 2 cubed is 8, so negative 8 plus 1 is negative 7. F of 1 would be negative 1 plus 1, so 0. F of, what else we got? It's negative 1 and 3. Yeah, it looks like. Negative 1. Negative of negative 1. Yeah, positive 1 plus 1 is 2. And then f of 3 would be, let's see, 3 cubed. That's 3 times 3 times 3. That's 27. So negative 27 plus 1 is negative 26. So A would be f of 2 minus f of 0 over 2 minus 0, which would just be f of 2 is negative 7, f of 0 is 1, 2 minus 0 is 2, it's negative 8 over 2, that is negative 4. B, 3 and 1. So f of 3 is negative 26. F of 1 is 0 over 3 minus 1. That's negative 26 over 2 is negative 13. And C, f of 1 is 0 minus negative 1 was 2 over 1 minus negative 1. So that's going to be negative 2 over 2 equals negative 1. So there we go. We have average rate of change from 0 to 2 average rate of change from 1 to 3, and average rate of change from -1 to 1. Only other type of problem they might give you is something like this. This is really the same thing, though. In 72, they have this function, x squared plus 1. They want you to find the average rate of change from -1 to 2. Well, if you look at that, g of -1 would be 2, because -1 squared is 1, plus 1 is 2. G of 2 is 2 squared is 4, plus 1 is 5. Alright then, find the average rate of change from -1 to 2. So g of 2 is 5. G of -1 was 2 over 2 minus -1. That's 3 over 3 equals 1. Find an equation of the secant line containing this. So let's see here. We were looking at x squared plus 1. That graph looks like this. 0, 1, 1, 2, 2, 5, -1, 1, 2, -2, 5. Now here's the graph. Here's the line between the 2 points we were finding the average rate of change of, between -1, 2, and 2, 5. Now the secant line is actually just this line. A secant line is a line that cuts off a curve. So we already have 2 points on the line, so it's actually pretty easy to find the equation of the line just using stuff we did back in 2-3. So we know we had the point -1, 2, and we had the point 2, 5. So then we had our slope came out to be 1. I think that was what it was. Let's see here. Slope came out to be 1 indeed. So all we got to do is build our equation of our line. Remember, equation of the line is y equals mx plus b. So y equals x plus b. And we just plug in our points. So plug in 2 equals -1 plus b. B equals 3. So our secant line is y equals x plus 3. So that'll be it for this video. And for this section. We'll start up next time with section 3.4. We'll talk about parent functions, or the library of functions, as I believe our book calls it, and talk about piecewise defined functions as well. That's where you have a function that's split up into pieces on its domain, and it behaves like different functions depending upon what part of the domain you're in. Have a great day, /evening, /morning, whatever it is. See you next video.